Hi, my name is Nahyuk Lee, and I'm from Pohang University of Science and Technology. Today I will present our work, Combinative Matching for Geometric Shape Assembly, which accepted to ICCV 2025 as highlight presentation. In this presentation, I'll share how we enable AI models to understand how 3D parts interlock, not just by looking alike, but by fitting together in a physically meaningful way. The task we address is called 3D Geometric Shape Assembly. Given a set of fractured or separated pieces, our goal is to recover each piece's 6DOF pose in 3D space, so that all pieces can be reassembled into the original object. This is a fundamental problem in areas such as reverse engineering, archaeology, scientific domains and robotics manipulation, where understanding how parts fit together is crucial. Several groups have proposed different approaches for geometric shape assembly. While each method has its own strengths and weaknesses, it's important to note that the core component across all of them is the matching module, which is responsible for establishing correspondences between parts. The parts we want to assemble are related to each other like male and female joints, or interlocking wooden pieces. When we look closely at the mating regions, they're not identical, but rather complementary. One part fills the other's empty space. However, previous methods assume that mating surfaces look the same, and therefore rely solely on visual similarity to establish correspondences. While this equative matching strategy is effective for registration tasks, but the assembly requires something beyond visual similarity alone. Now, what kind of matching do we actually need for assembly? Let's take a look at interlocking wooden joints, which are commonly used in civil engineering and construction. One important thing to notice here is that the male and female parts share some geometric similarities, but they are not identical. What's the same is the local shape of their mating surfaces; they fit perfectly in form. What's different is their local volumetric structure, or occupancy; they're opposite in how they occupy space. In other words, one solid region corresponds exactly to the other's empty region. Let's focus on this point here at the center. When we look at in terms of surface shape, these blue and yellow corner points should share the same local description, since the shapes fit perfectly together. However, in terms of occupancy, they should be exactly opposite. One lies inside the solid region, while the other lies in empty space. This observation motivates us to go beyond equative matching, and to design a new approach that considers both similarity and dissimilarity for robust correspondence learning. Thus we present new shape matching methodology, named combinative matching, maximizing the similarity between shape descriptors to ensure matching of geometrically similar surfaces, while simultaneously minimizing the similarity between occupancy descriptors. This complementary relationship reduces local ambiguity and enables stable and physically consistent matching between parts. Here is more details. We train our model to learn the descriptor for each point as follows. First, we enforce matching points to predict the same orientation. This is necessary for assigning shapes and extracting rotation-invariant features. Then, we extract rotation-invariant features from points and divide into two parts, shape descriptor and occupancy descriptor. For shape descriptors, we maximize similarity between matching points. For occupancy descriptors, we minimize similarity between matching points. When we do actual matching, we use shape similarity minus occupancy similarity as a final similarity. These three losses, orientation consistency, identical shape similarity, and volume occupancy dissimilarity, consist in the total objective for learning. Here is an example of learning, visualizing estimated orientation of points on mating surfaces. Our model learns meaningful orientation patterns without any explicit supervision. The x-vectors align toward the surface center, while y-vectors point inward or outward depending on convexity or concavity. This shows that our orientation objective helps the network naturally capture surface geometry and curvature. And this is showing top 100 correspondences using learned descriptors. Due to the shape ambiguity, shape descriptors produce a lot of false matches, colored in red. However, occupancy descriptor, used as negative similarity, successfully resolve this ambiguity, resulting in good correspondences. The overall architecture are designed in this way. We extract features, predict orientations, and learn two matching branches, shape and occupancy. Their similarities are combined through optimal transport, giving the final transformation matrix between two parts. Here, we compare our results with previous methods. As shown, previous methods fail when surfaces look similar but don't actually fit. But our method uses complementary shape and occupancy cues, achieving accurate and stable assemblies close to the ground truth. Our method, CMNet, consistently achieves the best performance across all settings, reducing both rotation and translation errors, outperforming previous state-of-the-art methods. To summarize, we introduced combinative matching, a framework that jointly considers shape similarity and occupancy complementarity for robust geometric assembly. By carefully leveraging geometric equivariance and invariance, our method achieves realistic, physically consistent part matching, and we believe this idea can extend beyond assembly to other relation-based 3D reasoning tasks. Thank you for listening. If you're interested, please visit our poster session on October 21st at Exhibit Hall I, booth number 885. Again, hope to see you in Hawaii.